let us have a nice easy introduction to the course. So sit back, relax and take it easy for the next 15 minutes, and I'll take you on a journey from a humble light bulb all the way up to an Intel Core i9 CPU. Now this isn't just contrived in order to make a good video, there is actually a connection between the light bulb and this processor. So let's continue with the journey. Now, although Thomas Edison was not the first inventor to work out the ideas of electric illumination, he was the first person to invent a practicable incandescent light that worked well and could be mass produced. He used a coiled carbon filament connected to platinum contacts. He filed his patent in 1879 and went on to form the Edison Electric Light Company. So let's have a look at this electric light bulb. Edison and his team worked on improving the incandescent light using carbonized bamboo filament. But there was a problem, that carbon from the bamboo would fly off and become deposited on the inside of the glass bulb. The carbon was coming from the end of the filament connected to the power supply, which we now call the anode. Edison thought that the carbon was probably charged and that electrons were not only flowing through the filament, but were also flowing out of the filament onto the inside of the glass and carrying with them the carbon atoms. Edison worked on various experiments to try and prevent the blackening of the inside of the bulb. After a certain period of time, the bulb would become so dark on the inside that the light would be very, very gloomy. So he had to try and work out a method of preventing this. So what Edison did was he made a special bulb with an extra contact or an extra electrode to try and see whether there was in fact current flowing from the filament onto the surface of the inside of the bulb. So when he put this extra contact in, you can see the contact here, it's a small strip. He found that indeed there was a current flowing from the filament across the gap onto the inside of the bulb. Now this extra filament, extra electrode, didn't prevent the blackening of the inside, but Edison recognised it as having potential, and he in fact patented this device. So what he had stumbled on was the beginnings of the first electric valve, or if we like, electric amplification. Now opposite here we see a more modern version of this electric bulb with the extra electrode, and this is obviously called a valve. So we have the glass tube on the outside, we have a heated cathode, so the central part is called the cathode, and the cathode is where the current or the electrons come from. In this instance here, the cathode would be the filament of this bulb. We have on the outer part the anode, and this is where the current would flow to. And in between we would have a mesh, and this mesh would be the part that creates the control, that is, it actually controls the flow of current. So these are the three different parts of this valve. We have the anode, the cathode and the mesh, but it's nothing other than a simple bulb with an extra electrode in it. So with the invention of this bulb with the extra electrode, Edison had stumbled on what is now known as thermionic emission or thermal emission. A hot cathode, that's the central part here, in effect is the filament of the light bulb, will emit electrons into the vacuum of this glass tube. So opposite here is the thermionic valve. We see the centrally heated cathode, and it will emit electrons, and these will be gathered by a surrounding anode. The third connection is made onto a grid. Now the grid allows us to control the flow of electrons from cathode to anode. So what we've created here is an electronic valve, and we're looking around about 1907. So if we look at the valve in plan view, that is from the top, we're going to have the anode on the outside here, which is where the electrons flow to. We're going to have the cathode, which is heated up, and that's where the electrons come from, and we have the grid, and the grid controls this flow of electrons. So what we have is a voltage controlled current source. The voltage on the grid controls the current from the cathode to the anode. So if we apply a positive voltage to the anode, it creates an electric field in the surrounding space, which attracts the electrons from the anode. So this is why it's called a field effect. Now this would be called forward biased. But if we reduce or apply a negative voltage to the anode, then the electric field opposes the electron flow. We have here then reverse bias. So this is a device that allows current to flow in only one direction, that is from the cathode to the anode. So what we have created here is a field effect device, which we could call a diode. So if we apply a voltage to the grid, then we'll have a three-terminal device. We'll have an anode, a cathode, and the grid. So this three-terminal device is called a triode. And the beauty of this triode is that it provides amplification. So we're going to have a voltage-controlled current source. Let's see how this provides us with amplification. Let's say, for example, we take the anode at 200 volts and the central cathode is sitting at 0 volts. Then between this point here and this point here, let's say that's 2 centimeters, then we're going to drop 20 volts every millimeter. So when you come in 1 millimeter here, it'll be at 180 volts, then 160, 140, 120, and so on all the way down to the cathode, which is at 0 volts. So let's say we now take the grid here, which is in purple, and we now put the grid at minus 10 volts. It means that the electric field associated with the grid can be added on to the electric field associated with the anode. So overall, the electric field is going to drop from 20 volts per millimeter to 20 minus 10, which will be 10 volts per millimeter. So that means that, in effect, the anode will now be sitting at 100 volts as opposed to 200 volts. Now we get the amplification because if the grid is close to the cathode, then a very small change in this grid voltage will create a much greater change on the voltage on the anode. And in this instance here, with this example, we're going to get an amplification of times 10. Now this is called the field effect, and this is a field effect triode. So here is a simplification of our voltage control current source. we're going to have a cathode where the electrons come from, we're going to have an anode where the electrons go to, and we're going to have this grid, or if you like to call it, a gate. And this gate controls the flow of electrons through the device. So a small change in the grid voltage G results in a large change in the current from the cathode to the anode. This large change in current can then be converted to a large change in voltage by the application of an external load. So what we have here is voltage amplification. And here is a schematic for the Triode vacuum tube. We've got the heating element, the cathode, the anode, and the grid. And here is a cross section of a triode valve. We have the heating element in the centre, we have the cathode in the centre here as well, the anode is on the outside of the casing, and we have the grid, which is a coil of wire. And here is the symbol for it here. Now, as we all know, we never get something for nothing. So the word amplification really could be replaced by the word control. So let's say, for example, we have an elephant here sitting in water, and this little man has been tasked to lift the elephant. The little man isn't strong enough to lift the elephant up, so he comes up with this little idea here. He takes a pipe of water and he has a valve, and there's like a little valve there. And the other side comes along, goes underneath the elephant. The little man only needs to apply a small amount of force onto this valve, which will release a lot of force up through to lift the elephant. So the amplification really comes as a byproduct of the idea of control. The little man controls a valve, which controls the flow. So by amplification, we really mean control. So why is amplification useful? Well, I think we all know about speakers, and we're able to amplify the noise to create louder volume. But there's another area to amplification, and that is when we use it as negative feedback. So this allows us to trade amplification for bandwidth, linearity, stability, and less distortion. Now this isn't really part of this course, and it's really part of an analog course. But what we have down here is a typical op-amp circuit using amplification and negative feedback to produce something useful. Now we are not going to use our valve as an amplifier. To look at that, we'd be looking at a course on analog circuit design. What we are interested in doing is we are interested in looking at our valve as a switch. Now we have to ask, why is switching useful? So by switching I mean just turning the valve on and off, the same as we would turn a light bulb on and off. Well, this is useful because we can create little logic circuits. So for example, I've got a Nand Gate and a NOT gate and a logic circuit. So we can see here that if we had a switch here, SW1, and a switch here, SW2, if both of these switches are closed, then we have current flowing all the way down through to ground, in which case we drop this voltage across the resistor, and it means that this point here goes low. So whenever we put a high input in here and a high input in here, both of these close over and this goes low. So two high inputs will give us a low output. Alternatively, if any one of these inputs here goes high, goes low, then one of the switches will open. If one of the switches open, then this point here will be pulled high. So what we would have here is a logic gate called a Nand Gate. Now we could work through the same logic here and we could produce a NOT gate. And here's another example where we take the Nand Gate followed by the NOT gate and we can produce an AND gate. So we can use our valves as the little switches. And what we want to be able to do is to switch really fast. If we can switch really fast, then we can join lots of these logic gates together and we can make them do very, very useful and interesting things. So for example, we can build every logic function that we need in order to produce a CPU using our valves. Now the ENIAC, that is Electronic Numerical Integrator and Computer, was completed in 1945, and by 1956 it contained 20,000 valves, 7,200 crystal diodes, 1,500 relays, 70,000 resistors and 10,000 capacitors. But the main point about this is it's produced using our valves, and our valves were nothing other than the electric bulb with an extra electrode. Ideally, we want our switching device to be reliable, small, easy to manufacture. We want it to consume very little power and be super fast. Now, the vacuum valve fails on all of the above. Now, one of the first people to consider something called a solid state valve was a guy called J.E. Lilienfeld. He considered the field effect device, but the field effect device built out of a material rather than built out of component parts. So he had no means to implement the device which he invented in 1925 because material science hadn't advanced far enough. It wasn't until 1947 that the first solid-state amplifier was built, and in effect this wasn't a field effect amplifier, it used a different process. It was called a bipolar transistor. Now this course won't be covering bipolar transistors, but we'll mention them now and again on passing. But just as a quick look at this, what we have here is a mock-up of the original device, and in the original device we had a mounting with a spring. We have a contact here which had a little gold leaf at either side. This was called the emitter. We had a germanium base and we had a metal contact at the bottom, and this had a tiny contact here, so the gold didn't go all the way around, there was a tiny contact at this point here. Now this device here allowed us to produce amplification, and it's down to these three guys here, John Bardeen, William Shockley and Walter Brattain, and they received the Nobel Prize in Physics for this invention. But we're really interested in the field effect transistor, so let's go and we'll see how the field effect transistor came about. Now the bipolar junction transistor was difficult to mass produce and miniaturize in the 1950s. Even now it tends to be used for primarily analog design, although we can also create digital blocks using, say for example, emitter coupled logic. Now this course is on MOS circuit design, and we won't talk very much about the bipolar junction transistor. So enter Mohammed Attallah. He was of Egyptian origin. Now he had the idea of coating a wafer of silicon with an insulating layer of silicon dioxide. So the gate would be insulated from the substrate, just like the gate in the grid in a valve, but it would still allow the electric field below the gate to control the cathode to anode current, the same as a valve does. So what he had invented was the metal oxide semiconductor field effect transistor, and we're talking round about 1959. So we have a voltage between the gate and the substrate. This voltage creates an electric field, and this electric field controls the current from the source to the drain. So we have a voltage controlled current source in the same manner as our humble electric bulb with an extra electrode. So what we have here is a MOSFET. So we have the metal on the gate, the oxide insulating layer, the semiconductor material here, so that's the MOS sandwich, and it's a field effect transistor, so it's controlled by the field effect of the gate to substrate voltage. Now the real beauty in the process of producing a MOSFET is the idea of modularity in mass production. We can take one of these devices and stick next to it another device and another, and in fact we can stick together hundreds of millions of them, and we can join them together to produce Boolean functions or logic functions, and ultimately we can use this simple structure in order to produce an Intel Core i9 processor. So this process here is compact, miniaturized, it can be mass produced, it's low power, it's scalable, high density, reliable. It really is all our dreams come true. So finally, here is our timeline from a bulb in 1879 to a valve 1907 to the MOSFET in 1959 and finally to an Intel CPU 2017. So that's the end of the introduction. I hope it's given you a pathway or an idea of the timeline of going from a humble light bulb up to a CPU. Now, thank you for listening. I'll get you on the next video. Goodbye.